nobody.
Too much pressure. Like you're not.
Yeah, how do they expect it to like?
Great question.
Did you see the video from 6 months ago of the
Get it set up.
Yeah, there's nothing. It's just a tube.
It's a video. Is that the signal? Oh, wait. I was getting the side.
Wait, what? They can't take it.
Yeah.
Should we use the microphone?
Yes, you should.
Okay, so for the YouTube recording, the microphone is needed. This is a test. This is not official. Oh, you have a nice one. Okay.
Well, no, I don't have this one. It belongs to the room.
So this is ours.
Yeah.
Great.
Okay, hi. Wait, is it? Okay. All right, we'll just get started. So, hi everyone. Welcome to the first summer colloquium. My name is Devashree Talpanini, and I'm a rising senior at Cornell University in Ithaca, New York, studying physics with a concentration in astronomy and statistics.
And my name is Phoebe Harritz. I am also an astronomy REU intern. I'm a rising senior at SUNY New Paltz in the Hudson Valley. I study physics and astronomy and have an applied math minor as well. Oh, sorry about that. So, as I mentioned, we're both astronomy interns here at the CFA, and we have the pleasure of running the first summer colloquium series. And I'd like to introduce our speaker for today, Dr. Daniel Castro. Dr. Castro is an astrophysicist here at the CFA, working as part of the Chandra Xray Center mission planning team. As a researcher, Dr. Castro studies supernova remnants and pulsar wind nebula, particularly using X-ray and gamma ray observations. He was born in Venezuela and lived there until he was 16, at which time he moved to Wales to finish his IB at the UWC Atlantic School. Remaining in the UK, he studied physics at the University of Edinburgh, where he received his bachelor's and his master's.
So after graduation, Dr. Castro returned to Venezuela and enrolled in a PhD program at Universidad Simón Bolívar in Venezuela. With almost no options for astronomy advisors there at the university, he became a Smithsonian predoctoral fellow at the CFA, working with Pat Slane, who became his thesis advisor and is now the director of the Chandra X-ray Center. And then after his PhD, Dr. Castro worked at MIT as the Chandra HETG postdoctoral associate before moving to NASA Goddard Space Flight Center, where he spent time as a visiting scientist and as a NASA NASA postdoctoral program fellow. And he finally joined the CFA as an astrophysicist in 2017 and has recently seen his first predoctoral fellow graduate. And aside from his research interests and active mentorship, Dr. Castro advocates for diversity, equity, and inclusion initiatives, serving on the CFA Council, helping lead the DEI Journal Club prior to COVID, something which he intends to start up again soon, and serving as the Fermilat DEI representative. So without further ado, please join us in welcoming Dr. Castro.
You guys can hear me, right? Through the microphone? Excellent. Hi. I didn't know I was going to be the first colloquium, so this is exciting. So I don't have to match up to the last week's presenter or anything like that. This is the greatest talk you'll ever hear during the colloquium series for this week. Maybe not for the entire semester. All right, awesome. So I'm going to talk to you about particle acceleration in the remnants of supernova explosions. But first of all, I'm going to go through a couple of things first. So Dev and Phoebe mentioned that it could be useful. Okay, great. All right. To tell you guys a little bit about my winding path through the world of physics and astrophysics. They give a really good summary of my academic path and how I got here, which is great. Thank you so much for doing that. So I'm going to go through this fairly fast. Feel welcome to ask any questions that you want during the talk or at the end. All questions are welcome. Overall, some people might think that careers in physics and astrophysics need to be this like straight path through academia. Mine was not, and I feel pretty happy with where I am at right now. So I would invite you to always consider sort of alternatives while you're going through this, difficult and perilous road, which I'm sure you're all going to succeed through and find your best place. So I started off living in Venezuela, the son of a couple of engineers. My mom is an electronics engineer, and my dad is a mechanical engineer. And physics was always part of what we talked about at home. Math was fairly easy in comparison to for like my fellow students who didn't have engineers as their parents and overbearing parents to start with. Extremely supervisory and checking out my homework before every day. It became like a very easy thing. So going into the sort of STEM fields seemed like a very natural fit. So I did that when I finished my IB in Atlantic College in Southern Wales, which is for most of you who you might not know, it's this hippie boarding school for international students on scholarships in the southern coast of Wales. Pretty magical place. It's like Hogwarts on the water. It's very nice. Right, so I finished that, and then I went to the University of Nottingham to do electronics engineering to make my mom happy. And then it turned out that I wasn't happy doing that. So after 6 months, I dropped out. It wasn't because I failed any subjects or anything like that. I just didn't enjoy it. And I figured, you know what? I'm just going to go back home, regroup, and find something that I like. And at that time, I decided, well, I like understanding how things work, but in the abstract. I want to be totally useless for the stuff down here on Earth, right? So what am I going to study? I'm going to study astrophysics. So that sounds great. And I just, I applied to, universities in the UK. Several of them said, yeah, fine, we'll have you. Edinburgh, again, was the most magical one of all of them, just in terms of like the landscape and the place. It's beautiful. If you've ever been to Edinburgh in the UK, you'll know this. If you haven't, go there. It's very nice, and the weather is not as terrible as the rest of the UK, or at least the rest of Scotland. And it was a magical 5 years where I got my master's in physics. And by the end of that, I was done with astrophysics. I was like, no, I'm not doing this anymore. I want to work on something different, something like, I don't know, making films or working for the UN or something of the sort. And then after 6 months, that I realized that there weren't all that many paths for me to do that, and that I did actually enjoy astrophysics. I was just a little bit sick of the stuff that I had been doing for a few years. And then I decided to go into my PhD in physics in Venezuela. I had spent about 9 years outside of Venezuela by that time, so I decided, let's go back to Venezuela. And then after 3 years, I said, okay, yeah, this seems like it's going to work out, but I don't have an advisor. I contacted a few people around the world just by emailing them. Email, super powerful. And several of them returned my emails saying, yeah, I would be interested to chat with you. And at that time, sort of FaceTime and all that stuff did not exist. I'm not super old, but I'm fairly old. Back then, there was no video calling people, etc. So I actually came to Boston and met up with a few people. I met up with John Hooker, who's unfortunately no longer with us. And he gave me a list of people here at the CFA to meet with on the basis of, first of all, they matched my interests in astrophysics, which was mostly high-energy astrophysics. And secondly, they had money to host me here. So I went and talked to all of them. They were all super nice, but Pat had the longest hair. And I felt, yeah, I went to this hippie school. This guy looks like a hippie. He's wearing a Beatles t-shirt. I'll go and work for him. And that's what I did. So it turned out to be a very lucky decision because, Pat has been an amazing mentor and advisor throughout my life. And that's what I did. I became a Smithsonian Predoctoral Fellow. And by 2010, 2011, I finished my PhD thesis. Pat actually traveled to Venezuela for my defense, which is slightly nerve-wracking because Venezuela is a very dangerous country. And I was like, oh, nothing can happen to him while he's here for this 1 week. Luckily, he came back happy and filled with like delicious Venezuelan food and chocolates and beer, etc. He loved his trip, so all was well, and I passed my defense as well. That's the secondary. That was the other good thing about that trip. And then I became shortly a postdoctoral research associate here just for a few months while I found somewhere else to go. I went to MIT as a Chandra HETG postdoctoral scholar. And after that, looking for, after spending 4 years at MIT, trying to find my second postdoc, I applied for an NRC fellowship to go to an NRL and do high energy astrophysics there as well. It turned out that I moved to DC, and on my first day at the job, I was told at the gate that I couldn't enter because I hadn't passed my security clearance. So this is the type of thing that might come up in your career, which at the time seemed like the end of the world. Seriously, I had left my wife here in Boston because she had a good job, and you can move down to DC whenever you want, and I'm more settled there. But I had moved everything down there, and then suddenly I don't have a job anymore. And the cycles for jobs in academia are kind of tricky, as you might know. So this was the 1st of October, and I was standing there in the middle of DC with no job anymore. So this became a problem, but this problem was solved very easily by me, again, calling people. This is my solution to most problems, right? Don't be afraid of calling people, talking to the people that you know and you like, and the people that have worked with you and know how good you are at doing some things. So I contacted the people at the Fermilab team in Goddard Space Flight Center, the NASA center, which is just outside of DC, and I said, listen, I have this problem. And they said, that's fine, we'll have you. We'd love to have you here. They found money for me in conjunction with George Mason University. I was an assistant research professor at GMU, which sounds like a really lofty title for someone that 2 weeks before didn't have a job. And yeah, so that put me through, I don't know, about 1 year at Goddard. Then after that, I got a NASA postdoctoral program fellowship to stay at Goddard and continue to work with the Fermilab people on gamma ray astrophysics. So that worked out really well after that 1 year. And then I applied to, I don't know, about 8 jobs here at the CFA, all to work with Chandra. I was put in about 5 shortlists, maybe 6. The story when you get put into a 6 shortlist is that the first 5 you failed, right? So the 6th one worked out. And I was eventually hired here as part of the science operations team, specifically the mission planning team, which is the team that takes care of scheduling all of the observations that Chandra does. And for those that don't know, Chandra is a space telescope. So I schedule stuff for the satellite to sort of turn around in the sky and look at that. Right. So that's how I came here. As you can see, not the most straight, direct path through academia, but it worked out for me. I'm happy. I like what I do. And as long as nothing hits Chandra in the next couple of years, everything should be fine. Everything should be fine. That's what I keep on telling the bank with the mortgage and everything. Right. So since I mentioned Chandra, something's happening with the font when I'm going to have to apparently move backwards and forwards because the font, sort of the text disappears every time I move forward. I'm going to talk to you guys a little bit about Chandra first before I talk about actual research. There's 2 reasons for that. Well, first of all, I work for Chandra. And secondly, Chandra is going to turn 25 years old next year. It was launched in 1999. And it continues to be the premier X-ray telescope in the world. And if you ask ChatGPT what is the greatest X-ray telescope ever built by humankind, it will say Chandra. And it'll give you a nice little snippet of why. I didn't quote it here. I thought that was going to be cheesy, but I already told you, so that's kind of cheesy. So first of all, why study the sky in X-rays, right? So the short and skinny of why not to study the sky in X-rays is, first of all, X-rays don't come through the atmosphere, which is good for our health, but it's bad for observing X-rays from outside, right? So that's the first problem. And secondly, we get far fewer X-ray photons from anywhere than we do optical photons or infrared photons. Radio emission is much larger in flux than X-rays are. So why study it? Well, it turns out that there's a large part of the universe, the most energetic, the most explosive, that basically emits mostly in the energy range of X-rays. And it provides us with a window that no other wavelength does, right? So I'm going to get you through like one look at it. For example, right now we're looking at an observation done by Tycho Brahe of the sky in 1574, when the star that appears as I, you'll see that in the little glossaries, I is a nova stella, it's a new star. This is a supernova explosion observed in the optical. They actually just looked up at the sky and you could actually see it in the sky. This is new star. We have named it Tycho because Tycho found it in 1574, or really it's SN 1574. And this is what the field looks like today in optical observations, right? Not particularly exciting. And roughly, if you want to know where I was around here. Right around where that star is, but not quite where that star is. But if you look at it in the X-rays, that's what you see, right? That is the extremely hot plasma of the supernova remnant of the 1574 supernova. As it expands through the CSM, the circumstellar material, and the interstellar material, and compresses it and heats it to X-ray emitting temperatures. And this is what we see. We see emission from the extremely hot Bremsstrahlung emission from the electrons. We see emission lines from all the different ions in the plasma. That stuff is shown in red. And in blue, we see the synchrotron emission from non-thermally accelerated electrons at the shock interacting with the local magnetic field, right? So it's twirling around in the magnetic field at extremely high velocities, very relativistic electrons, and they emit synchrotron emission, which is non-thermal in nature. And you can see it there in blue. And the way that, we show you this in red and blue this is not real colors, of course. It's just we chunk up the energy that we get from the supernova remnant into different bands. And we say, okay, so this band is dominated by thermal emission. Let's show that in red. This band is dominated by a non-thermal emission. Let's show that in blue. And that's why I'm showing you that, right? So that kind of answers a little bit the question as to why observing in X-rays. Now, really quickly, going through my sort of sales pitch of why Chandra, it's just amazing. So this is Chandra, the instrument part, just the instruments, right? The science instruments. This is not the actual telescope. It's where the instruments went, being built originally. Actually, I don't know where this picture is taken. I should know that. Apologies. I do know. TRW. Is that one's TRW? Yeah, that makes sense. And this one is in Kodak in upstate New York, where they were building the mirrors, right? And you can actually see the concentric mirrors being built here. And the reason, for all of you who have, again, who have done any X-ray astronomy, you'll know why concentric mirrors are necessary for X-ray observations. It's because a normal mirror to observe optical emission will reflect light that way. The problem is that X-rays will go right through a perpendicular surface that they find, most perpendicular surfaces that they find. And this technique was developed a while back into how to focus X-rays into science instruments. And of course, by the way, most of you know that Jonathan is an absolute expert in X-ray astronomy. So if you guys have any questions that I don't answer today, please feel free to ask him all the questions that you want. So this is basically a diagram of how the X-ray mirrors work, and they manage to focus X-ray photons. So this is the whole thing put together. The solar panels come out perpendicularly. They are always pointing towards the sun. This is the main shaft. The mirrors are in this region here, and the science instruments, which is a whole set of 4 different science instruments, are all in the background, right at the back. In terms of scale, just to give you the scale, this is roughly the size of a school bus in terms of size. So this thing was really, really large. As a matter of fact, it was the largest payload to get up on the shuttle when this was launched, right? It was launched in 1999. That is working, so we have a video of launch there on the left. And over here, the whole thing has failed now. You see, I told you, something weird was happening. Okay, hold on. Did not like the video. All right.
To be fair, that's almost what happened to the space shuttle.
Okay. All right. So apparently I have to put my. Let's just say quit and reopen. All right. Hopefully that'll work. Maybe now it's going to work better than the first time. That is telling me to leave the CFA at this point, which I probably shouldn't. Right. So we're getting back to the video part. Let's start here. Okay. And there we go. That's the video. So launch is on the left. The mission was captained by Eileen Fisher, and the payload was actually released by Katie Coleman, mission specialist, who basically unleashed the whole beast. That was not the end of the journey for Chandra to its actual orbit, because its actual orbit is not near the Earth. It had a couple of other propulsor systems that would actually push it out into the correct orbit, which takes it out almost past a third of the distance to the moon. And then it comes back fairly close to Earth on its 64-hour orbit, roughly 64-hour. And then we go, see, very exciting, the rocket launching. Excellent. Right, so as I was mentioning, this is what the orbit looks like, and the orbit sort of evolves through time, like all things that are not in L2 or L1 do. Very exciting, excellent. Right, so doing astrophysics with Chandra. So what kinds of things can you study when you're using Chandra? Well, I'm just giving you some examples here. There's a lot more science that you can do with Chandra, but I'm showing you stuff like Jupiter, I believe, over there. That is Jupiter, right?
Yeah, that's the aurora of Jupiter.
The aurora of Jupiter. You can see the optical image and the aurora shown in purple. The aurora is observed by Chandra, in both poles of the planet. Here you see a pulsar wind nebula, which is fairly famous. That's a crab, which is a pulsar rotating very fast and producing this very large wind of particles that arranges itself and gets confined by the magnetic field around the pulsar. And you can see all kinds of shapes in the crab. You can see a jet coming out of the thing. You can see a torus around it, and you can even see some other structures. And you can understand highly relativistic particles and particle acceleration very well. There's a planetary nebula over there with an AGB star in the middle pushing out some plasma. Helps you understand certain parts of stellar evolution and how AGB stars interact with their medium. Getting to much larger scales, here we can see an image of the Perseus cluster taken with Chandra as well. So this is one large cluster of galaxies. And most of what we see here, instead of the galaxies, is the intercluster medium, the really, really hot plasma around all the galaxies that are forming that particular cluster. And in this case, we can see the X-ray emission from a couple of galaxies and the bridge that joins them. Now, I'm going to focus on 3 highlights. One in our galaxy, supernova remnants, not surprising. A little further away, active galactic nuclei, and then we're going to talk about really, really large-scale things like galaxy clusters. Right. Okay, so starting with in our galaxy. So this is Cas A. Cassiopeia A is a supernova remnant. It's a little bit older than Tycho, but it's unlike Tycho, is a result of a core collapse. I'm going to go over those terms a little bit later. Cas A is a very well-studied supernova remnant. It's super interesting. This is what the previous best image of Cas A was before Chandra launched. And this is what it looks when you observe it with Cas A with Chandra for a significant amount of time. Again, the coloring corresponds to what we've chosen the different energy bands to be, and that's the amazing thing about the spectral imaging abilities of Chandra, which is you can actually chunk up the band into things that, for example, show you only the emission lines from silicon ions in red. So anything that you see here that is red is dominated by silicon emission, the sulfur emission, calcium emission, iron, and the blast wave, which is mostly the synchrotron emission that I mentioned before. Now, why is that interesting in a supernova like Cas A? Is because it actually tells you things about the explosion mechanism, and it tells you about the star right before it blew up, right? Because it tells, where the iron is right now. It's telling you something about where the iron was at the time of the explosion and what the explosion shape and the mechanisms behind the explosion were. Not going to go into too much detail about that, but nonetheless, you guys, I'm sure, can see how that's important. So AGN, so supermassive black holes and their jets. So this is one of the first images that I think Chandra took of an AGN. Originally, people thought, oh, crap, we screwed up the optics. This was meant to be a point source, and now we see this thing screwing up on the side. It turns out that Chandra was so good at observing this AGN that you could actually see the jet extending outwards from it. PKS phone number is the name of this particular.
0637-752.
Bravo. I have it written here. That's the only reason that I know he just got it right. Right, and this one is M87 instead, which is a little bit more famous. And in a second, those that don't recognize that name will recognize the picture. But this is M87. You can see a bunch of structure around this very active galaxy. This is a close-up of the Chandra observation. You can clearly see the jet. And now, so that you guys can recognize why this is famous, is because M87 was the first black hole imaged with EHT. And basically, you can see basically where that image came from with EHT. So this is the black hole, and that huge thing is the jet that is coming out of it. Right, and finally, just to mention something about really, really large-scale stuff, studying clusters of galaxies uses X-ray observations in a very, very important way for many different purposes. And I'm just going to talk about one way in which it's proved very, very important, but how clusters of galaxies are connected between themselves, how galaxies are connected amongst themselves, how clusters of galaxies collide is super important in our understanding of dark matter and how dark matter is located all across the universe. And here is a really, really, really super result from Chandra observations. and I'm going to describe this really quickly. So the background stuff that you see, all the sort of point sources and galaxies, those are optical images, right? And those optical and infrared images have been used to turn their shape information into information about where the dark matter is located from gravitational lensing of those images of those galaxies, right? And the way that that's represented in this image is by those blue purpley circles. That's actually a derivation from the gravitational lensing presumption that tells you where the dark matter in these clusters of galaxies is located. It turns out that these two clusters of galaxies have just collided, and by just, of course, I mean billions of years ago. But the funny thing about this image is that when you look at the X-ray emission, which is telling you stuff about actual baryonic matter rather than dark matter, you can actually see that it's completely different shape, that they did interact between them. That's telling you these two things really did collide, right? This stuff is almost got like a bullet shape in terms of its collision, but the dark matter itself does not show doesn't seem to register this collision, right? And that is telling you something about how dark matter collides with itself. Basically that it doesn't, right? And that's a really, really important result. Right, so back to Cassiopeia. Still playing with the text because it disappears. Well, first of all, why should you care about the connection between supernova remnants and cosmic rays? That's what I'm going to be talking about a little bit today. What evidence is there that supernova remnants actually accelerate cosmic rays? And what can we learn from a multi-year study of Cassiopeia with Chandra? Now, that's all very good and interesting, but first of all, I'm going to tell you a little bit of things, well, a few things that you should know about supernova remnants before I move on to talk about this actual research project. And this is basically going back to Cassiopeia and talking about stuff that I actually do in terms of research. So this is my primer on supernova remnants. So supernova explosion is the explosive end of a star, right? Two main types, core collapse supernovae, basically a very, very massive star, larger than 8 solar masses, eventually runs out of fuel to keep it from gravitationally collapsing, and the whole thing blows up. Leaves behind either a black hole or a neutron star, and if that neutron star is spinning very quickly, that's just going to be a pulsar. The other type is a thermonuclear explosion, usually known as a type 1A type of supernova. And those are most likely the result of the interaction between a white dwarf and another body. One channel is that it's the actual collision with another white dwarf, so two degenerate stellar objects colliding. Or the other system could be a white dwarf that has accreted material from a normal main sequence or very, very large, some type of other stellar companion that basically accretes its material onto the white dwarf until that white dwarf reaches the Chandrasekhar limit and collapses gravitationally. Now, those types of explosions don't leave behind a compact remnant, so they don't leave behind a black hole or a neutron star. The whole thing blows up and it all turns into ejecta and moves upwards. Like this one, which some of you might recognize because even though the coloring is different, that's still Tycho, the Tycho supernova remnant. Now, why am I showing you this picture? We've already gone through this stuff. Oh yeah, so this is what a supernova looks like. Very unexciting in comparison to a supernova remnant, right? It's just basically a dot of light. It's very exciting when you look at the timeline, and it's very exciting when you look at the spectrum because you learn loads of things about how the thing blew up. And we don't actually observe that many supernovae from our galaxy. The last one that happened was hundreds of years ago, even though we expect to have several of them every 100 years. Most likely these are happening in areas that are obscure to us, so somewhere in the galactic plane. The optical light is not actually reaching us. Supernova remnants, which happened hundreds of years ago, have already expanded on these large chunks of things that are really, really hot and are not obscured by things that obscure optical emission. Now, in terms of structure, really quickly, so basically after the thing blows up, all of this material is like ejected outwards. As you eject material outwards into the circumstellar material or interstellar material, it'll basically push it outwards really, really fast. That basically is a shock. So you can imagine your hand moving through water and pushing it out, and it's big, you have this like ripple of water right in front of you. That's the shock, and it's sort of compressing and heating the material around it. Now, there's an important part of a supernova remnant, which is the reverse shock, and this one always gets people. It's kind of hard to get your head around a little bit, but it's basically a shock that is moving inwards in relation to where the ejecta ends. And why is a shock moving inwards? You can think of this as basically a car crashing onto a wall, okay? The forward shock, so the stuff that is moving outwards, is the stuff that is moving into the wall because it just found out that a car crashed against it, right? So it heats up, it breaks up, etc. That's the mechanical and thermal shock of the car hitting the wall. Now, the way that the taillights find out that the car just crashed into a wall is because the car, the things that make up the car, eventually start transmitting the information backwards as we're not moving ahead anymore. So basically, your velocity needs to change very fast, right? And that sort of transfer of information backwards actually moves as a shock backwards. And it does compress and heat up the material the same way as a forward shock does. And you might think, well, why do you need a reverse shock to heat up the ejecta? The ejecta must be really hot, right? It was part of a star, and then it blew up in this thing. Well, it turns out that it adiabatically cools very, very quickly. So a few years after the explosion, it's already gone to very, very low temperatures. So it needs the reverse shock to actually sweep back through it to heat it up to X-ray emitting temperatures. Now, the spectrum of the particles that are in a supernova remnant, basically you have this Maxwellian bump here, which is what we call the thermal component. It depends on what velocity the shock is moving at. That will control what temperature the plasma is at, and that stuff is the thermal stuff. And then there are particles that don't just cross the shock once. Don't get dispersed by the shock once, they get dispersed by the shock several times. How do they do that? Well, they recross the shock. They get caught in the shock because they hit off ripples in the magnetic field around the shock. Sort of that diffusive shock acceleration can become very efficient when you have a very strong shock, and you end up with this tail of non-thermal particles that move towards the really, really high energies, because every time it disperses off the shock backwards and forwards, it gains a lot of energy. So that's how you get particles to be non-thermal, and those are particles that are, to the right in the energy band, in the energy axis here. You can see that the thermal stuff would just end here, but you get this extra bit of particles over here. Now, that was the particle spectrum. This is the photon spectrum from a supernova remnant. And this varies. This is just a very vignette-y way of showing it. You have synchrotron emission, starts in the radio, moves through IR, visible light, UV. It can move into the X-rays, as I'll show you in a second, depending on the conditions around it. But it's basically those non-thermal electrons interacting with the local magnetic field. This thing that looks a little bit like a porcupine, the underlying curve is Bremsstrahlung emission, thermal Bremsstrahlung emission from the electrons that were accelerated by the shock. And the lines are the ions in that plasma as they lose energy from the excitation they emit in those wavelengths in emission line form. And that's what we observe mostly in X-rays in thermal emission. And then in the gamma ray band, you get three different emission mechanisms. You get inverse Compton of the CMB. So again, the same non-thermal electrons that are doing the synchrotron emitting, they're hitting off the CMB as well and transferring their energy to the photons and then bumping them up to gamma ray emission. And then you can observe that in gamma rays. Pion decay, which is the only one that is really purely hadronic here, which are basically instead of non-thermal electrons, it's non-thermal protons that get accelerated at the forward shock. And those collide of local protons that are just cold and sitting there. And they become a meson, a neutral meson in the way, it's a neutral pion. And that neutral pion eventually decays into gamma rays. And we can actually observe it. And it has a very particular shape because it erases very quickly from here. And this energy is actually basically the energy equivalent of what the rest energy of a pion is. So basically, you don't get any pion decay below that because a pion would not have that low an energy. And then finally, non-thermal bremsstrahlung, which is equivalent to the thermal bremsstrahlung from the same electrons, but in this case, talking about the non-thermal electrons that were accelerated. Now, if the particle spectrum that you have, that non-thermal emission that I showed you to the right before in the particle spectrum, it has a cutoff that is higher. So basically, you have particles that get to recross the shock many times. Then the synchrotron emission can actually move all the way into the X-ray band. And we observe that in many cases as well. And other things that change the synchrotron emission are, for example, the magnetic field strength around the supernova remnant. And if you increase the magnetic field strength, then you increase the amount of synchrotron, and you actually move it also further into the into higher energies. All right. I have no idea what's happening. Okay. So why is the connection between supernova remnants and cosmic rays important? Well, cosmic rays are a really interesting question. We don't know what the origin is. They actually form most of the gamma ray background that we see. So understanding where they're accelerated is actually a fairly important question for gamma ray astrophysics. Particle acceleration, we need to understand how shocks accelerated particles. So understanding them in supernova remnants is, well, supernova remnants are a great laboratory to understand particle acceleration. They tell us a lot about the supernova remnant evolution because, as you can imagine, losing energy by accelerating particles is basically energy that you don't have available to heat up the plasma to thermal emission. So it actually plays an important role in the evolution of a supernova remnant. And also because cosmic ray feedback has proven like an important component of galaxy evolution models. But I'm not going to go into much detail about that. Now, in terms of the non-thermal X-rays that I mentioned before, and I'm going into basically the evidence of why we know that supernova remnants are accelerating particles to relativistic energies, and we think that might be the origin of cosmic rays. First of all, the shock structure, not going to go into details about that, but it's just basically, as I mentioned, the evolution changes, and we see changes that sort of indirectly tell us that supernova remnants are indeed accelerating cosmic rays. Non-thermal X-rays, this is very exciting because, you know, if you see synchrotron emission, you know you have relativistic electrons. The only thing, the only ding on that part of the evidence is that most of the cosmic rays that we observe on Earth are protons or other hadrons, right? And as I mentioned about 1 million times at this point, synchrotron emission comes from relativistic electrons, not from protons, right? So we know that they're relativistic electrons, but we still haven't proven that these shocks are accelerating protons to cosmic ray energies. But it's not only the synchrotron emission, also the magnetic field amplification that we can measure in some of the supernova remnants is, again, indirect evidence that supernova remnant shocks are actually accelerating particles to cosmic ray energies. And finally, gamma ray emission, as I mentioned before, can show you that you have relativistic particles, but then again, it has turned out that telling apart leptonic emission, so emission from relativistic electrons and relativistic protons, is fairly difficult. So we haven't been able to nail that question from the gamma ray band perfectly clear. So one example of how we measure the magnetic field strength from synchrotron observations in supernova remnants is this example of, this is a core collapse remnant core RxJ1713. These are several different observations with Chandra, and you can see that there's some synchrotron emission that appears in 2000 that basically has disappeared by 2006. In this case, you have an observation in 2000. 2005, you see this nugget of synchrotron emission, and by this point, it has already gone. And the fact that that synchrotron emission has that variability in time scale is telling you something about the magnetic field strength that is around where those electrons are losing their energy due to the magnetic field, right? Because you have an electron that gets accelerated to a certain energy, but then it radiates away that energy in a certain time scale, and that time scale is governed by the magnetic field. And in this case, we found that the magnetic field strength around this remnant must be something around 1,000 microgauss, which is a huge number if you consider that the ISM's average magnetic field strength is around 3 microgauss. And you expect the shock to compress that magnetic field by a factor of about 4. So at best, you're expecting the magnetic field strength to be around 10, 12 microgauss. This is 100 times larger than that. So that actually turns out to be fairly robust evidence that the magnetic field is getting amplified at the shock of a supernova remnant. And in order for the magnetic field to get amplified that way, the only way we have to explain that is through cosmic rays, protons being efficiently accelerated at those shocks. Because it turns out that the magnetic field that I mentioned that was dispersing the particle several times to recross it, etc., that magnetic field turbulence is created by the cosmic rays themselves, particularly the protons. Right. So, moving on really quickly, trying to find more evidence of magnetic field amplification. Here's some of the evidence that has been shown up to now. These are X-ray observations of 3 different remnants, and you can see that the filaments of the X-rays are very, very thin. It turns out that the width of the filament can be connected also to the magnetic field strength. Why? Well, if you can think about this, the simplest way possible is you have this acceleration site right at the shock, right? And the electron has gained all of this energy and is going to radiate it away in a certain time, right? The higher the magnetic field, the shorter that time is, right? Because you lose more energy because the magnetic field is making you lose energy faster, right? So the thinner the filament, the higher the magnetic field. And these are fairly thin filaments, and basically the calculations from those filament widths have turned out to be factors of amplification of about 100 to 150 in many cases. So those are fairly compelling. Now, what I'm going to talk about is this, a study that we did on Cassiopeia. And as I mentioned earlier, Cassiopeia has been well studied by Chandra throughout Chandra's history. So we have about 20 years worth of observations of Cassiopeia. The best one was in 2004. We made several different observations that add up to about almost a megasecond of time on Chandra. And that's where that really beautiful image of Cassiopeia that I showed you before, that's where that comes from. But the fact that we've actually tracked it through the years can tell us a lot about not just the filament and their width, but also the velocity at which those filaments are moving. And those are actually really important pieces of information when you're trying to tell apart, when you're trying to understand how the magnetic field has been amplified in those remnants. Now, what I'm showing you here is basically an image of Cassiopeia just in the really in the non-thermal regions, so the hard part of the spectrum. And we can see it expand very slowly. It actually doesn't show up as clearly to the eye until the thing jumps back from 2018 to 2000 when it contracts really quickly. But yeah, and also this image is not well registered because I didn't actually need to register the image. And by register, I mean making sure that they are exactly on the same frame of reference, all of them. And the reason that I didn't need to do that is because I'm interested in looking at each of those filaments around the supernova remnant and calculating the width and also calculating the distance from this central compact object, which I know how fast it's moving and in which direction. So can actually take that into consideration. And that's why I didn't need to make sure that all my edges were well aligned, is because I could just extract a profile and I know where the central compact object of Cas A is located at. Now, in the stuff that I'm going to show you today, I'm just going to show you about, I think it's the results from about 15 filaments. I've expanded this project to about 52, which is a bit of a nightmare because it turns out that now I am extracting profiles for about 1,400 observations, but that's fine. This is an example of what they look like right at the edge. You can actually see the width of the filament, and you can actually see it, how it's moved. So the red one is from 2004 and the blue one is from 2018. And you can see that it's fairly easy to extract the displacement there. This is the same rim, rim 32, with throughout its Chandra observations. And this is basically when you put it together, and each of the vectors is showing you the longer the vector, the faster it's moving. And the structure of Cas A and why some of those are a little bit slower than others is an interesting question, but we're not going to go into that. The most important results are actually summarized in this image, which is basically the velocity of each of those filaments and the width. It's in the y-axis. Now, as I mentioned before, you can connect the width to the magnetic field strength. But in order to do that, it's really important to know what the filament's velocity is. And that's why this project is really, really useful, is because you know exactly the velocity of the filament from observations of the very filament that you're measuring the width. In many cases, this has been done with other information about velocity of the shock. We found that the rim velocities ranged between 4,000 and 7,000 kilometers per second, which is pretty fast even for a supernova remnant. The velocity structure is not all that important for this part of the talk, but a really interesting thing is that the width estimates of 1 arc second to 5 arc seconds basically result in estimates of magnetic field strengths of about 300 to 900 microgauss. So again, we are fairly certain that Cas A's shock has actually accelerated particles to extremely high energies, most of them protons, and they have created this magnetic field amplification right at the shock that basically multiplies your magnetic field by factors of 50 to 100. A really interesting thing is that you can see that the width increases with the velocity. And again, the text has, there we go, magically they appear. So there are two ways in which the width can be given by the width is controlled by the magnetic field, right? So one of them is that the width is given by advection, which is the simple case that I explained earlier. Basically, your electron gets accelerated and loses energy very efficiently, and then the furthest it moves, the lower your magnetic field is. So the velocity is actually a part of that equation. But then there's the diffusion length, which can also dominate the filament width. And that diffusion length either doesn't depend on the velocity of the shock. This is a bit of a debate in the field. It has to do with the acceleration mechanism and the acceleration timescale. Or it can not depend on the velocity of the shock at all. So it's either inversely proportional to the velocity of the shock, or it doesn't actually depend on it at all. And this plot actually shows that in this case, we're pretty certain there is advection that is the mechanism that is giving you the filament width. And that way, we are sure that the way we're connecting the filament width to the magnetic field strength is actually a fairly robust one. So, takeaways. Large variations in the forward shock of the velocity of Cas A. That tells you that the remnant is fairly uneven in its evolution, and that mostly depends on the on the change, well, basically on the shape of the explosion and also on the shape of the CSM, of the circumstellar material. And that the width of the synchrotron filaments in Cas A seems to be correlated to the velocity of the rims, and that seems to suggest that this is advection that is at play here. And also, it's fairly solid proof that there is magnetic field amplification right at the forward shock of Cas A. And this other more cavalier statements are a little bit more in the weeds. We might actually be seeing some narrowing of the filaments. As you remember, the widths seem in that sort of close-up of one particular rim, they actually seem to be different widths. That's actually fairly interesting. That might mean that your magnetic field is actually getting higher magnetic field strengths throughout time. And some rims might actually show that they're actually slowing down, which is also interesting. And I am going to leave it there.
All right, thank you, Dr. Castro, for that wonderful talk. At this time, we'll take some questions if anyone has any.
I'm not sure, but is your
I don't
microphone
think
on?
it's completely on.
Okay.
But
All right.
yes.
Right.
I wanted to ask, what material are the mirrors made out of on Chandra? Or do we have to make them out of a certain material in order to accommodate that change of shape?
That's a good question. So, Jonathan, they are made, basically, I think they're made of glass and then they're covered on gold.
I believe
And
that
iridium?
the coating for the mirrors themselves is iridium. if I'm
Iridium,
not
right?
mistaken. But you can also use gold, and in fact the gratings use gold in their facets. So the point is that you need a heavy atom, because if you make your reflective material out of a crappy little atom like carbon, the power of the X-ray, right, is going to knock it out of the way instead of reflecting.
Thank you.
Sure.
Any other questions?
So you show all the spectral of the supernova remnants earlier
Mhm.
on the gamma ray section. I see there are 3 different contributions overlapping into each other.
Sure.
In reality, when we observe it, how do we decompose this?
We can't. It's unfortunately it's one of those things that we can't totally decompose. So I don't have an actual gamma ray spectrum from a supernova remnant here. But this particular,
how do you know the different contributions?
so this particular feature, the fast rise of the pion decay bump is actually it plays a really important role. Fermi-LAT is the only telescope up to now that has been able to observe down to about 100 MeV, which is right where this rise is. And basically you can see that if you see a spectrum that looks like it's rising very quickly and then flattening out, instead of something that is just rising steadily, then you have pion decay, right? Because inverse Compton cannot mimic this shape. So you know that it's basically cosmic ray protons that are doing the emitting by interacting with the local medium. Now, the problem is that the spectral resolution and the background for Fermi-LAT in this region is at its worst, because that's, of course, how life works out, right? Right where you need your best observations or your best observational capabilities is where you don't have them. So future missions in the gamma ray band, such as Amigo is one of the proposed missions for the future, that's the mid-X, are actually going to focus on getting better spectra right there. But yeah, that's how you would be able to tell them apart. There's basically 4 remnants in our galaxy that we have determined that they are for sure pion decay emitting. That's the only way we can explain that gamma ray emission. It turns out that they're really, really old supernova remnants interacting with very, very dense molecular clouds. And that makes sense, because if you have a molecular cloud, you have a really large target of protons for your relativistic protons to head off, become neutral pions, and then decay into gamma rays. So the higher that density, the more gamma ray emission you're going to have from pion decay. The problem is that when a supernova remnant hits a molecular cloud, it slows down really, 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 really quickly, right? And the slower your shock, the less cosmic rays you're producing. It turns out that we believe that those 4 supernova remnants are not actually freshly accelerating cosmic rays, but instead they're re-accelerating the already existing sea of cosmic rays that is in our galaxy by basically pinching them. And that's a complicated explanation that we can go into offline if you want.
Thank you.
Like, at what point in your wonderful background did you kind of decide you wanted to focus on X-ray specific astronomy? Like you said, you applied to only Chandra specific positions here. How did you narrow that and come about that?
It came from before. I mean, that's the kind of thing that sort of ends up working out during your PhD, and you can expand. Like I started working on X-rays basically because my PhD advisor, who was Pat, explained, sat with me for an hour and a half and explained to me things about supernova remnants that I didn't know. And he's an expert in X-ray observations, and I thought, well, this is what I want to do with my life. But it turns out that, for example, I have this second career in gamma ray astrophysics, which ties very nicely with X-rays because they're both very high energy. But that came about because someone from Fermilab approached Pat and said, listen, we need a student to come out here to Stanford for a few months and start working on supernova remnants in the gamma ray emission. And he was like, oh yeah, I have a student. I'll send him to Stanford for a month. I was like, good weather. I mean, new skills. What could go wrong? So I went out to Palo Alto for a month, and I became basically, at that time, the expert on supernova remnants that did Fermilab observations outside of the Fermilab collaboration, because I didn't become a part of the Fermilab collaboration until 2015, when they were happily absorbed the competition into the thing. So it's basically like a merger at that time. Jonathan?
So these SNRs accelerate cosmic rays. We see cosmic rays here on Earth.
Yep.
I guess for the neutral ones, do we have some can we tie which cosmic rays come from which supernova remnants?
No. So it turns out that that's actually one of the problems with understanding where cosmic rays have been accelerated, right? Is because they are so high energy that none of them are neutral. They're all charged particles. And as you know, the magnetic fields all across our galaxy and even outside of our galaxy deflect charged particles. I just spent a while talking about synchrotron emission, but not even from synchrotron emission, but from just deflecting them and changing the trajectory, it makes it really, really hard to pinpoint with the cosmic rays that we observe here where they came from. So we have to turn over to the photon emission because that's going to tell us things more like straight, especially if they got accelerated right at the site of acceleration. If they got emitted right at the site of acceleration. But yeah, that's a good question.
I think we're out of time, so let's give Dr. Castro another round of applause. Thank you for joining us in our first summer colloquium.
All right. Thank you very much for inviting me. Thank you,
course.
John. And thank you, Matt.
And next week, same time and place, we'll be hearing from Dr. Jaya Metil, who's also at the CFA, and she's going to be talking about AGN orientation and how to solve for supermassive black hole masses and accretion rates.
And then 2 weeks from now, I'm going to embarrass you. We're going to get Hannah talking